In this video, we will discuss how to find the domain of the radical function. A radical function is a function that contains a radical expression. If the index is an odd number, then there are no restrictions, and the domain of the function is a set of all real numbers. If the index is an even number, the radicand is restricted to non-negative real numbers. The domain of f is a set of all real numbers where the radicand is greater than or equal to 0. Let's find the domain of f. What's inside the square root has to be greater than or equal to 0. To find all values that can be an input of f, we solve the inequality x plus 4 is greater than or equal to 0. Subtract 4 from both sides. Therefore, the domain of the function is a set of all real numbers greater than or equal to -4. To plot this on a number line, we place a shaded circle over -4, since x can be equal to -4. X can also take any value greater than -4. We shade the number line to the right, towards positive infinity. We can write our domain using the interval notation. We use an open bracket for the shaded circle and a closed parenthesis for positive infinity. The interval notation will be -4, positive infinity. Solve for the domain of this function. Here, the radicand is a second-degree polynomial. To find its domain, we find the zeros of the polynomial x squared minus 3x plus 2. An easy way to do this is by using the quadratic formula. A quick recall of the quadratic formula. If ax squared plus bx plus c equals 0, then x equals -b plus minus square root of b squared minus 4ac all over 2a, with a not equal to 0. In our equation, a equals 1, b equals -3, and c equals 2. Solving for x equals 3 plus minus square root of 9 minus 8 over 2 equals 3 plus minus square root of 1 over 2 equals 3 plus minus 1 over 2. X equals 4 over 2 equals 2, and x equals 2 over 2 equals 1. The zeros of our radicand are 2 and 1. After finding the zeros, we do a test in the number line. If the radicand is greater than 0, the interval is included in the domain. Otherwise, it is not included. So let's do a test for -infinity, 1. Let 0 take the value of x. X squared minus 3x plus 2 is 2, which is greater than 0. Therefore, the interval is a subset of the domain. For 1, 2, let x equal 3 over 2. X squared minus 3x plus 2 equals 9/4 minus 9/2 plus 2 equals -9 over 4 plus 2 equals -1/4, less than 0. 1, 2 is not included in the domain. For the x's greater than 2, let x equal 3. 9 minus 9 plus 2 equals 2, which is greater than 0. The interval is included. Therefore, the domain of G is the union of -infinity, 1 and 2, positive infinity. See this last example, where the radical expression is in the denominator. We will have two restrictions. The radicand must be non-negative, and the denominator must be non-zero. X plus 3 is greater than or equal to 0. Subtract 3 from both sides. X is greater than or equal to -3. For the second restriction, we solve the inequality. Square root of x plus 3 minus 2 is not equal to 0. Add 2 to both sides. Square both sides. Subtract 3 from both sides. x should not equal 1. We place a shaded circle over -3, draw an arrow towards positive infinity, and place an open circle over 1. We can express the domain as -3, positive infinity, excluding the singleton 1, or using the set builder notation, set of all real numbers greater than or equal to -3 and not equal to 1. If you'd like to see more YouTube algebra tutorials, check the links in the description. If this video helped you, give it a thumbs up. And don't forget to subscribe to my channel, Math Marvel. See you in my next video.